welcome to this explainer. I'm host 1, and I'm here with host 2. We're going to take the abstract and, honestly, kind of intimidating math of quantum mechanics and translate it into a physical, intuitive reality. Our goal? To help you absolutely crush your upcoming exam.
Yeah, if you've been staring at bracket notation until your eyes cross, you are in the exact right place. So let's just jump right in.
Okay, here's our game plan. We're going to ascend in complexity, starting with basic states and unitary evolution, then hit the measurement postulate, composite systems and entanglement, the density operator, and finally culminate in a literal quantum protocol heist, superdense coding. All right, kicking things off with Section 1, States and Unitary Evolution. We're looking at the geometry of quantum reality, basically establishing the actual physical meaning behind all that standard notation. Before we even look at the math, I want you to picture reality like this. Think of the state vector as perfect GPS coordinates for a quantum system. You know how GPS gives your exact location on Earth? Well, this unit vector in a complex Hilbert space tells you literally everything there is to know about that system.
Exactly. And for your exam, make sure you explicitly state this. The normalized vector contains all possible information. And hey, the fact that it has to be normalized, that just physically guarantees the object actually exists. The total probability of finding it somewhere is 100%.
So, how do these GPS coordinates change over time? That's Postulate II, evolution. Think of unitary evolution as a perfectly frictionless clock ticking forward. It is flawlessly predictable, and because there's absolutely no friction, it's perfectly reversible.
Right, no information is ever lost. That's what that U dagger U equals identity equation actually means. Don't just read the symbols, realize that this mathematically guarantees the total probability stays at exactly 1 as the system evolves. It's a closed, perfect system.
And these gates right here, these are the actual gears inside that frictionless clock. We have the poly X doing a bit flip, the poly Z doing a phase flip, the Hadamard creating a superposition, and the C0 entangling 2 qubits. Look at these for your exam, but don't just blindly memorize the matrices. Remember why they work. Postulate II guarantees that applying any of these unitary gates is completely deterministic. If you run a system through a gate, you can always apply its exact inverse to completely undo it and get your original state back. Moving on to Section 2, the measurement postulate, when observation shatters superposition. We're going to slow way down right here. I want you to really notice the stark physical contrast on this slide, because this is exactly where examiners love to dig for lost marks. Evolution, what we just talked about, is this smooth, predictable flow preserving all superposition. But measurement is a sudden, violent, completely irreversible shatter. Evolution preserves all possibilities, but measurement forces the universe to pick just one, destroying the superposition instantly. Which brings us to Postulate III, the completeness relation. Seriously, don't let the Greek letters freak you out here. What this equation is actually telling us is that when you measure a system, the probabilities of all the possible outcomes absolutely must sum up to exactly 100%. The universe doesn't just misplace a particle during a measurement, it simply forces it into a single, concrete reality. And the crucial takeaway is what happens after the measurement. Listen, for the exam, you have to define measurement as probabilistic and irreversible. You aren't just passively reading a value, you're fundamentally altering the state.
Right. The state permanently collapses to the observed outcome, divided by the square root of its probability. And why do we divide it? To mathematically force it to remain a valid, normalized GPS coordinate. Once you measure, the glass is shattered. There's no going back.
All right, let's step up the complexity with Section 3, Composite Systems and Entanglement. We're looking at a shared reality now. Imagine a pair of magic dice. Normally, in the classical world, rolling one die has absolutely zero impact on the other. But what if rolling a 6 on the first die instantly, magically guaranteed a 6 on the second die, defying every rule of classical probability?
That bizarre shared reality is exactly what Postulate IV calls a tensor product. The state space of a joint physical system is the tensor product of its component spaces, which is what allows these deeply linked, entangled states to exist in the first place.
So how do you tell them apart? Well, if a state is just a product, like Alice has a 0 and Bob has a 1, it's separable. They're independent. But if that joint state cannot be factored apart into independent pieces, it is officially entangled. And the absolute ultimate examples of this are the 4 maximally entangled Bell states. Big exam call out here. State very clearly that entanglement means the math simply cannot be factored into separable parts. And please absolutely memorize all 4 of these Bell states. They're basically the standard currency for quantum protocols. That brings us to Section 4, the density operator, navigating incomplete knowledge. So far, our neat little isolated vectors assume we know exactly what's going on, but the real world is messy. Let's set a scene. Imagine your lab partner prepares a qubit and sends it to you, but they trip over a wire and totally forget to tell you if they prepared it as a 0 or a 1. You don't have a quantum superposition here. You just have good old-fashioned classical ignorance.
Exactly. This creates a huge gap in our toolkit. When we lack complete knowledge of a state, the standard state vector totally fails us. That's why the density operator becomes our inevitable mathematical solution. It's built to handle quantum probabilities and classical ignorance at the exact same time.
To be a valid density matrix, which we denote with the Greek letter rho, it has to pass 3 tests. And these are not arbitrary rules. They are physically inevitable. First, it must be Hermitian. That just guarantees our probabilities are actual real numbers, because an imaginary probability makes 0 sense. Second, the trace must equal exactly 1, which guarantees our probabilities sum up to a full 100%. And third, it must be positive semi-definite, meaning no negative probabilities. For the exam, you have to list all 3 of these conditions to correctly define a valid density matrix. Okay, and here is your rapid-fire exam punchline. How do you actually know if you have perfect knowledge or incomplete knowledge? You square the density matrix, and you take the trace.
Yep, if the trace of rho squared equals exactly 1, boom, pure state, you know everything. But if it's less than 1, that represents a mixed state of incomplete knowledge. It is a brilliant binary test, and examiners absolutely love to use it.
Let's pull everything we've learned together into Section 5, Superdense coding. This is the quantum heist, and for this applied masterclass, we are literally going to become our 2 characters. I'll be Alice, encoding the message.
And I'll be Bob, decoding it. Let's steal some bandwidth.
Our heist begins in phase 0 with a pre-shared secret, the E-bit. We start with 2 isolated, perfectly boring zeros. First, I apply a Hadamard gate to qubit 1 to create a superposition. Then, we apply a C0 gate to link them up. Boom! We now share a maximally entangled Bell state. You keep your qubit, Alice, I'll take mine, and we're going to head to opposite sides of the planet. Now, I want to send Bob a 2-bit classical message, let's say 01. Normally, I'd have to send 2 entire particles, but by applying a local gate, in this case, just the poly X bit flip to my single qubit, I am mysteriously steering our shared remote joint reality into one of the 4 orthogonal Bell states. I literally didn't touch Bob's qubit at all, yet the global state of our system has fundamentally shifted. Next is phase 2, transmission. I take my single solitary qubit, put it into a fiber optic cable, and physically shoot it over to Bob. By transmitting just this 1 physical qubit, I'm basically handing him the key to unlocking 2 classical bits of information that are hiding securely within our entanglement. And now, I, Bob, get to decode it. I hold both qubits now. To read the message, I simply apply the exact inverse of our preparation circuit, 1 gate at a time. First, I apply a C0 to unravel the entanglement. Next, I hit it with a Hadamard. This cleanly unravels our shared Bell state back into isolated, readable classical bits. I measure them, the wave function shatters, and out pops Alice's 2-bit message, 01. We transmitted 2 bits by sending only 1 particle. Hold on a second. Did we just break the laws of physics? Did we communicate faster than light?
No way. For the exam, unequivocally state that this protocol does not violate faster-than-light communication. Remember phase 2? Alice still had to physically transmit her qubit to me through a cable, which is strictly bound by the speed of light, and without her qubit arriving, my isolated half of the entangled pair looks exactly like a completely random, maximally mixed density matrix. Entanglement enhances the capacity of the channel, not the transmission speed.
Okay, take a screenshot of this cheat sheet right now. It perfectly synthesizes our ascending complexity today. We went from the firm foundation of perfectly predictable state vectors and frictionless unitary evolution straight into the irreversible shatter of measurement. Then we expanded into the tensor product of entangled composite spaces, used density operators to handle our classical ignorance, and finally applied every bit of it to the superdense coding protocol. As you head into your exam, I want you to consider this. If we can literally double classical communication capacity with just a single simple entangled pair, what other unimaginable realities and broken classical limits are hiding inside the vast exponential geometry of Hilbert space? It's a wild thought. Study hard, trust the physical reality behind the math, and you are absolutely going to crush this exam. See you on the next explainer.